USA-DFW Chapter Annual Convention, fourth symposium. Today, the Technology Symposium, focus on technology fusion, trend for the future. In today's world, technology transformation has created significant and fast changes. Many jobs require multidisciplinary skills. So our next two speakers will share with us about their work and shine some insights on the future industry trends. Please type your question in the Q&A box in the Zoom window. I will summarize the question in the end of the speaker's talk. Our next speaker is Professor Changzhi Li. He is a professor and Whitaker Chair in Electrical and Computer Engineering at Texas Tech University. His research interests focus on microwave and millimeter wave sensing for healthcare, security, energy efficiency, and human-machine interface. He received the prestigious American Society for Engineering Education Frederick Emmons Terman Award. This award is only given to only one professor in electrical and computer engineering every year in the United States. So it's a very prestigious award, and let's welcome Dr. Li. Dr. Li, could you share your screen?
Sure. Thank you, Dr. Chow, for the introduction. Can you see my screen now?
Yes.
Excellent.
Could you put it into presentation mode?
Yes. I guess it's already in presentation mode now, right?
Yes, correct.
Okay.
It starts.
Wonderful. Okay, good afternoon, everyone. It's my great pleasure to be here this afternoon to spend the afternoon with the CIE-DFW chapter. So to begin with my presentation, I'll briefly introduce myself as well as my research group at Texas Tech University. So I actually came to the United States in 2005, and I was very lucky to join Dr. Zhenshan Ling's group at the University of Florida in Gainesville. And when I was a PhD student, I regularly commute to Austin, Texas in the summer to do summer internship in Austin, Texas. And I really loved the life in Texas. Because of that, right after graduation in 2009, I joined Texas Tech University in Lubbock, Texas. So Texas Tech University was established in 1923, located in Lubbock. Currently, it has slightly more than 40,000 students. And Texas Tech has reached the status of designated Hispanic Serving Institute, HSI, a couple of years ago, although we are also a national research university. So my research group currently has 9 PhD students, and our research interest is radio frequency sensing, localization, and modern radar. And a little bit of Lubbock, Texas. So Lubbock is located in Western Texas. Besides football, we have 3 other important things. Wind turbine, of course, and below wind turbine, we have a lot of oil wells. And below the oil well, we have those white field. They are actually cotton fields. Actually, around Lubbock here, this is the world's biggest Egyptian cotton field. And my topic today is going to be related to radar and microwave. So I'll begin with radar. Actually, radar is an acronym coined by the United States Navy in 1940 during World War II. It stands for radio detection and ranging. So conventionally, radar gives us an impression of scary and expensive, bulky instruments. But today, my talk will be completely different. And about microwave, I guess for microwave, a lot of people, the first thing popped into our mind is this microwave oven. This is actually one small application of microwave. As a matter of fact, microwave is defined as a form of electromagnetic radiation. Pretty much it covers any EM radiation with wavelengths from 1 meter to 1 millimeter. And talking about the technology, I will actually play a short video to introduce what is the radar we work on. So allow me just switch into my, sorry for that.
Sure, take your time. And I would like to tell everybody that this is Dr. Lee's daughter.
Yes, that's right. Okay, there we go. So the video was taken more than 5 years ago. One night, I brought a device developed by my student back home. After my daughter and my wife went to sleep, that was my research time. I placed the device over there on the crib, and the device was looking at my daughter using radio frequency signal. So on the other side, on the laptop, you will see two waveforms. On the top is a time domain waveform showing her respiration and heartbeat. And on the bottom is simply a spectrum. So basically, what we've been working on is to using radio frequency signal to detect very tiny, gentle movements related to human activities. And this is the only page with a lot of theory. Basically, we send out a radio frequency signal. Once the signal reaches the body, it's going to be reflected. So our sensor captures the reflected signal, compare it with the transmitted signal. And if we do the things right, in the baseband, we will have two outputs, and each channel will have signal related to the movements induced by respiration and heartbeat. Okay. And here in this detection, one important thing is it's very low power. Actually, the signal power transmitted is a lot lower compared with cell phone signal. Also, we don't have to continuously turn on the transceiver. Instead, we can simply sample the movements using a very low duty cycle. So this is definitely safe to human subjects. And what we have seen over there, we call it Vital-Doppler effect, which was induced by vital signs. Another important radar detection is based on Micro-Doppler. And shown here is a simple example. If we have a person in front of the radar device sitting down, raise the hand, put the hand down twice, then you will see on the right-hand side, on the spectrum, we can see the signature caused by those body movements. And if we analyze it using advanced signal processing technique, we can pretty much tell what this person is doing. On the bottom side is another example of a person walking away from the radar, inducing a negative Doppler, and then push-pull hands twice. Over there, you can see something related to the hand movements, and then walked back towards the radar. So leveraging this Micro-Doppler effect in recent years, the industry is really doing very well. Google introduced this Google Soli concept. Basically, they use very small integrated radar device to remotely monitor how human hand move. And with that, they can achieve non-contact control of smart device. And the last version of Google's cell phone actually integrated this radar device to monitor hand gesture. And with that, you don't have to touch the screen. You can interact with the cell phone. And behind the scene, the most important thing is actually the semiconductor technology enabling all of this. So a lot of semiconductor companies are doing really good job producing small, low power sensor device. A lot of them are integrated chips. For example, Texas Instruments has its very well-known 77 gigahertz system for IoT and automotive application. Infineon is headquartered in Europe, and they have been working on 60 gigahertz gesture recognition radar, and they have been collaborating with Google, providing hardware for Google. Analog device also has 2477 gigahertz system for different applications. So the photo here shows a exhibition a few years ago, 2017, those companies demonstrating their device in International Microwave Symposium. On the other hand, people are also working from system level. So for example, IMEC is a research-oriented big company headquartered in Europe. And they have been testing this type of smart radar sensing device and application in office environments, public environment, and sometimes home environment. And talking about this technology, we must also talk about millimeter wave. So millimeter wave is a portion of microwave which has a wavelength that is shorter than 1 centimeter, so in millimeter wave range. And basically, this is a higher frequency range of microwave. Because we push the frequency higher, we have a smaller wavelength, and then we have a higher sensitivity to pick up smaller motion. So on this page, we actually have an example of a 125 gigahertz millimeter wave radar on chip that can detect mechanical motion as small as 95 nanometer. So this is quite impressive. And for this demonstration, the setup has to be placed on optical table to decouple any undesired motion due to people walking around that is coupled into the system because the motion is too small. And using the system, we were actually able to further detect human talking. So in this interesting demonstration, we have a millimeter wave radar, the same radar placed on the table, pointing towards the throat of this student, and he was saying, "I am a boy." So as you can see, using different signal processing methods, the radar can truthfully recover what he was saying. But in the meantime, the microphone from the cell phone actually detected not only "I am a boy," what he said, but also environmental noise produced by the ventilation fan. So basically the demonstration here tells us millimeter wave radar can help us with directional detection and get rid of environmental noise. And furthermore, in the future, you can imagine wherever the radar points to, you can actually pick up what a person is talking about. So moving forward, we also looked into how to use radio frequency millimeter wave technology to do mapping in complicated indoor environments. And in this demonstration, we have a radar placed in the center of the room, and the radar actually scanned for 360 degrees. And after that, you can see a rough image of what is going on, what is laid out in the room. But what is really nice is our radar can pick up vital signs and life activities of human subjects. So if you switch the radar to that mode, you can see in those two directions, there are strong life activities. So if you combine the signal together, you can achieve this human-aware localization. Simply detect where the humans are and get rid of the influence or the interference from the environment. The next demonstration tells us the radar not only detects human that is sitting still, but you can also track the activity of people walking around in a room. So in this demonstration, we have colorful graph. The y-axis represents time and x-axis represents range, which means distance between the subject and the radar. So as you can see, as time goes by, there is one human subject walking away from radar and then walked back towards the radar. The second example has two people walking pretty much in opposite direction, back and forth. Okay, and in the results, you can also see vertical stripes, which represent things that are not moving. And this is very understandable because in indoor environments, we always have other things like tables, chairs, those we call them clutter. Okay, so you may wonder, with a lot of clutter, will our radar or microwave technology really work? The answer is indeed yes, because we not only have distance information, but we also have speed information. So in this live demonstration, there are two human subjects walking back and forth in a very crowded environment. Obviously, we have a lot of clutters if we only look at the range change, okay? But if you combine range and the speed together, the lower left window, we are plotting Doppler speed and range, then you can see those two people walking back and forth, and all the clutters become this zero speed clutter line. So with that, you can track people pretty easily, even in complicated environments. So leveraging that, we can apply this to healthcare or improving human quality. So one simple example is fall detection. Imagine if a person is falling towards radar, then the distance from the human subject and radar will reduce, which means the range is reducing, right? And the speed of falling will increase. So the Doppler will increase from 0 to a high value. In the meantime, the radar cross-section will reduce because the person eventually will lie down. So you will be expecting on range Doppler domain a signature fading in this way. On the other hand, if the person falls away from the radar, the signature should be opposite. As compared with a jump, you will see a complicated pattern, which is definitely different from the previous two. So here we have experimental results demonstrating indeed this is possible. So the top line shows the pattern of signature fading away as the person falling towards radar. Middle row is the person falling away from radar, and bottom row is a small jump. And as security becomes more and more important in our society, people are also looking into how to make our society safer with radio frequency technology. So one application is active shooter scenario. The state-of-the-art active shooter detection device looks like that. It's based on ultrasonic or infrared. Basically, they detect the flash or sound after a shot is fired. And obviously, this is not effective in preventing this type of thing from happening at the first place. So the radio frequency sensor people have been working on recently try to address the issue from different angle. So imagine if a person hides a gun in the body, then he or she may have a very different working pattern. And the RF signal can detect the gun even if the gun is hidden underneath a big jacket. So here, our student actually performed some experiments to demonstrate how it works. So in this experiment, we have the same person carrying different things walking in front of the radar. And we are analyzing the radar signature using Micro-Doppler, the bigger graph, as well as range Doppler. So one thing is, if the person has a gun, the tip, a metal piece, is gonna produce a strong reflection on the Micro-Doppler, which is isolated from the majority of the signal. So if you compare this graph with the other graphs, definitely this is different. Okay. However, this could be confused with the person walking with the stick because that's also the metal piece. So if you look at the range Doppler, now the difference happens. The gun is hidden, the range covered is pretty small. As compared with that, you have a large range coverage. So researchers further applied machine learning, analyzing those signal pattern and demonstrated indeed it is quite possible to do this with radio frequency technology. And there are startup companies pursuing commercialization of this. The next example is also quite interesting. This was actually discovered by a high school student, Rachel Che. She spent one summer in my lab, and what she did was she compared the radar signature for a person in a car as a driver did different things. For example, dancing with the music or falling asleep. We were able to demonstrate the radar signal, again, could be quite different. So after Rachel joined MIT for her bachelor's degree, another PhD took over the work. So he further applied machine learning algorithm to the signal and demonstrated this type of activity classification in attentive driving behavior detection can be achieved with the help of computer completely automatically. Okay. So enough talking about detecting things that are moving. Now let's shift the gear a little bit. Think about the case the radar is moving. This is actually not new. So in the past few decades, military people have been mounting radar on airplanes and they fly over a big space. Leveraging the big path in the space, they can synthesize a very high resolution antenna radiation. And with that, they can get high definition graph of geometry. This is called remote sensing. But in our case, we mount our radar on drones and try to use this to help search and rescue after, for example, fire happens, there's a lot of fog, you can see things clearly, then you can fly a drone in and use radar to detect people. So here's a very simple demonstration. We have a drone with radar mounted, flew from left to the right, and using conventional SAR imaging, SAR imaging technique, we can detect what is in front of the radar flying path. Furthermore, if we leverage in heartbeats and respiration, that type of life activity, we can differentiate between human subjects and other objects and achieve human-aware localization. Okay, and besides moving of targets, moving of radar, we also want to look into how to move the radiation beam, the signal of radar, and that finds a huge application in transportation industry. So today, if you buy a car, you're gonna have lane changing assistance, blind spot detection, adaptive cruise control. All of them really benefits from radar. So modern cars has multiple radars inside. But the next step is gonna be how to make the cars even smarter. How do you detect a pedestrian, and how do you make completely automotive and reliable perceptive system? So with that being said, we want the radar to be able to steer the beam and look at the environment even for 360 degrees. So here is one simple example. If we have millimeter wave radar with multiple channels, and by controlling the signal difference among channels, we can synthesize a narrow beam and we can steer the beam to cover different angles. And with that, with a single radar, we can get a graph of what is inside in front of it. Again, leveraging a difference of movement pattern between human subject and other things, let's say a vibrating engine, we can differentiate between human and other objects and eventually achieve a pedestrian-aware mapping system for cars. And next page is a slightly better system. So here we have a three-dimensional MIMO digital beamforming radar. Basically, the beam can steer both horizontally and vertically. Since we also have range information, we can realize truly 3D detection. And in this demonstration, there are three small objects with different angle, different height, different distance, and we will clearly see those differences. Okay, and the next topic I want to briefly cover is how to cooperate with radar, because till now we are talking about a radar detecting anything in front of it. Another use of radar is we can collaborate with radar. And a simple example is a nonlinear radar that has been widely adopted. If you are interested in skiing, you probably have heard of this record tag. Basically, you can find it on your snow jacket or on your snow gear. And what happens is if a person is buried underneath snow, the rescue person can use the device. Pretty much that's a radar sending out signal at one frequency, but this record tag is a nonlinear tag. It's going to change the signal frequency to another frequency, sending it back. By doing that, the rescuer can actually tell what is the signal from really our victim versus signal reflected by other things like snow or other clutters. So this is one simple application of nonlinear tag cooperative operation. And this has been commercialized a few decades ago and widely used in national park and skiing places. But in our lab, what we are trying to do is to further make the tag smaller. So here are two examples, a small tag that we can wrap around the wrist. And by doing that, we can precisely pick up the pulse at the human wrist. And another example is we can make a wearable tag and plug it into the coat or whatever this person is wearing. And use that, we can pick up the heartbeat waveform from human subject. Okay, so my final quick topic to cover is security, which is becoming more and more important. So the reason we also look into security today is because there is a potential that some ill intentioned people may leverage radar detection, but produce a device that mimics the signature of human subject or the desired target, right? And we call this spoofing. Basically, you can use electronic device to synthesize a faked target and confuse radio frequency or radar detection system. So here's just a very simple demonstration. We have a radar system over there. We have a human subject, a corner reflector, and this is a spoofing device. And on the measurement result, as you can see, the spoofing device is able to produce a very strong reflection and confuse the radar, letting radar think this is the most important target in front of it. So there are also researchers dedicating new efforts into how to make radar systems stronger and more reliable, robust against malicious attacks. And one approach to do that is to invent more complicated radar waveform so that the spoofing device cannot follow what is going on with the radar. Okay, and finally, some industrial and R&D outlooks. Basically, there are a lot of companies pursuing radio frequency and radar imaging and sensing applications. For example, Alculi has been working on radar imaging, and they have been working with a lot of automotive companies to implement this in cars. Aptiv is formerly known as Delphi Automotive PLC, so they are producing devices for car companies in the United States. And Onder is a very interesting company in Austin. They have a lot of veterans from Texas Instruments, and they are producing digital automotive radar so that cars can perceive more, okay? And other applications include through the obstacle imaging, flood and coastal monitoring, and structural health monitoring. So with that, I'll conclude my talk today. Again, thank you so much, and I really enjoy the opportunity to be here this afternoon. Thank you.
Thank you, Changzhi. We have some questions. The first question was from all these parents who are concerned about their children's future. I can imagine that working on sensing radar in the past, it was electrical engineering job, but you are combining the radar for sensing in security, in healthcare. And so what is your outlook that for the future job markets in this field?
I think the future job market is actually quite attractive. And I was a little bit surprised by that because traditionally radar has been a military topic or a weather topic. So there is not really a big market for radar engineers. But in recent years, because of the push on healthcare as well as automotive application, we have seen companies aggressively recruiting people with radar experience or knowledge. For example, I have a few students doing internship this year, and it seems it's quite easy for them to get an internship. And in some of the startup radar companies, even fresh graduate students could become the leader, for example, hardware leader for radar sensor device development. And also I heard from my students, even those companies who are doing really well in this market, this future market, their engineers have a diversified background because in the past, there were not so many people working on radar. So a lot of engineers in those companies are also learning radar signal processing, fundamentals of radar. And as a result, even for fresh graduates from university, if the research was related to radar, they can find important roles in their companies. So this is slightly different from a lot of traditional work Like after graduation, you enter the job market, you go to a company, you have to become a student again, learn from senior engineers. But seems to me, in the radar job market, you can immediately become a key person in the team.
That's an excellent point. Actually, I have a lot of engineer coming back to school from automobile industry and try to learn about how electromagnetic and radar work. So that really is manifesting that a new job market is opening up and is involved more disciplines. In your research, you topic two very different directions for healthcare monitoring vital sign. That is the main purpose for the radar is you can protect privacy, unlike a camera. On the other side is try to provide security that can identify active shooter. How do you find the balance between these two? There may be more AI machine learning you involve. You can identify what people are carrying. Then that will be there may be a concern for the privacy.
That's right. That's right. And thank you for mentioning AI. Actually, AI is a very important aspect of modern radar. So after the preliminary signal is grabbed, a lot of advanced signal processing is required. And it really depends on how the signal is processed. The same radar front end could find different applications. As you just mentioned, healthcare, privacy preserving application versus applications that are more aggressive in protecting the safety, but may involve some privacy gray area over there. So indeed, it takes efforts to balance that. And for different applications, then the efforts could be completely different.
Yes, it's always tough choice balancing this for engineer. We have one question about what do you think is the main barrier to prevent a large-scale commercialization of this application discussed in the talk?
Oh, thank you. That's a great question. So the main barrier preventing large-scale commercialization, again, this really it has different answer for different applications. For example, for healthcare application, my personal opinion is the safety is really one big concern because radar is using electromagnetic wave, or you can say radio radiation. Then a lot of potential users may have the concern, is this safe? Is this healthy? Just like people have doubts regarding the use of cell phone. So in the presentation, I mentioned that our device actually transmits a signal power that is more than 1,000 times weaker as compared with a conventional cell phone. But it happened to me when I explained this to other people. I once met a person and he said that, oh, even cell phones, we don't trust it. We just had a baby, and we made sure when we made our new house, our router is placed really, really far away from the baby's room. So I think one important thing is really persuade, or I would not use the word of persuade. I would say maybe demonstrate or really prove this technology is 100% safe to the users.
Thank you, Dr. Lee. Could you share the screen?
Yeah, sure.